비디오를 아까 계속 녹화해서 올려줄까? 대답 안 하네. 그게 더 좋은가 봐. 나 수업 안 해. 나 지금 가서 녹화할래. Okay, double bond means chlorine. One chlorine at 1,2 position. Okay, that's a reduction. So the Fe to the double bond. 이렇게 아니야. 하나만 선택해. 잘못 눌렀나? Okay, that's a scene addition going together. Cis and trans is a different problem. Cis and trans happens to cyclic bond depending on other structure. It can be cis or it can be trans. The key point is on the plane with adding together synergy. Right? 1분 시간 준다. This is a hydration reaction, and hydration reaction usually acidic condition and water. Acidic condition, protonation happens and hydroxyl attacks, and that gives you OH group addition reaction with the Markovnikov rule added to more substitute position. Right? That's regular. That basically describes the same reaction. And mercury reaction is oxymercuration, mercury and reductive workup, that is Markovnikov. And hydroboration gives you the opposite of the product, and workup is oxidative workup. 이게 알킨 반응에서 거의 키야. 이거 들렸네. MCPDA. 메타클로 벤조이c acid. Okay, that makes it similar to H2O2, hydrogen peroxide, that add 1 oxygen, and that forms 3-membered ring, so-called epoxide. Okay, where's the pole? gives the two oxygen together, so that generates the 1,2 alcohol.
녹화 방송한 거
반도 못 맞, 딱안 맞췄네. It's generating carbene and CH2 tung carbene, and that is added to the double bond. It forms alkane. Specifically, what structure it generates? Cyclic, intermediate. What is the final product? Cyclic, propane. It forms cyclic propane, right? So it's a kind of alkane, but it's a cyclic form, and it forms this cyclic propane. What's the name of this reaction? It's a named reaction, right? Somebody's name is added to the reaction. What's the name of the reaction? It's one of them. There are two person there. 아씨, 누구야? 아씨, Simon Smith reaction. 오이. Simon Smith reaction. Okay, that generated this carbon and make that cyclopropane product. Ozonolysis by adding ozone and break up the double bond and then giving oxygen each. Okay, that generates the ketone as a product. Permanganate, strong acidic condition. Strong oxidizing conditions. Okay, let's look at this later. Iodate. That react with one, two hydroxyl groups. This react with this and generate open product. Okay, good. That's the problem. Okay, the same type reactions. 신을 해본 사람이 다 쓰면 돼. 대충 절반쯤 따라 보이는 것 같은데. we just started the reaction. So reaction of alkene. 여기서 헤매기 시작하면 2학기까지 헤매. 그래서 정리하면 들어간다. 자, 봅시다. Okay, double bond. Double bond has extra electron. So that's why it's a nucleophile. It has an extra electron. It gives electron. It meets with the acid, halogenated acid. Then electron rich that react with the proton first, and it generates carbocation as intermediate. And then any nucleophile attack behind. So that's anti-addition. Protonation happens one side and nucleophile attack behind. 1H, 1X addition reaction product is this. Right? And Markovnikov. More substitute position is modified by the nucleophile because carbocation is more stabilized there. Okay, that was the basic. Mixed with the halogen. Then, even though there is no proton, this cleaved heterolytically X plus, X minus. Okay, X plus is added here first, similar to proton. So it forms polonium intermediate. Has a preference, but anyway, it is intermediate, cyclic intermediate, and X minus attack behind. Anti-addition. Okay, so that gives you, looks like 1,2 halo, but anyway, that's anti-addition. It's similar to HX additions. Okay. How about here? If you add water, then first step is the same. But water amount, maybe compared to halogen, is much more excess. Intermediate is a carbocation. Carbocation is very reactive. It doesn't matter whether it's a good nucleophile, bad nucleophile. If there's a water is small, most likely large numbers, then intermediate is the same, but water attack rather than X minus. Okay, number wins. Then you get 1X, 1 hydroxide. Okay. Again, anti-addition. This one formed originally cyclic polonium, water attack behind, push this up. Anti-addition. Now, similar reaction to that, similar to acidic hydration. So we learned Mercury method and boron method. Mercury method is very similar, just to replace the proton. Make it easy and make it mild condition. Hg, this is acid, and then added here, and water attack behind. And the product, Markovnikov product, similar to acidic water. Okay, workup was reductive workup, hydride workup. If it's an oxidative workup, Hg, in this case, H minus attack and then replace this Hg. If you add an oxidative workup, like hydrogen peroxide, then you will get OH here. So that much you didn't learn. Okay? So I will not confuse you. If you see Hg, okay, you don't need to think about much for the workup part. Single hydroxylation, Hg attached first, water attacked behind, Markovnikov. Okay? And in comparison, hydroboration. H and BH2 added first. And then that BH2 is replaced by oxygen. That's oxidative workup. Reductive workup, hydride. Oxidative workup, hydrogen peroxide. In this case, more hindered position means more crowded position is preferred by proton, and then this goes to less hindered position. That's why less substituted position has hydroxyl as the product. That's the opposite of regular one. That's why we call this anti-Markovnikov product. Okay? How about this? Easy. Reduction. On the plate of metal surface, hydrogen is activated in the same direction, double bond approach, and then catch both of them. Syn addition. product is HH addition. Okay? So that's a reduction. Using metal catalyst and He2 addition. Okay? Now, oxidation. This is an example of MCPBA. But if you look at this, key point here is OOH. That's a key point. If you change the other part, the RCO, basically this is like this, peroxide. Hydrogen peroxide, the water soluble. And it's not organic soluble. To make this organic soluble, you can change with anything. Okay? That's one of the examples. And MCPBA, M-chloro, 4-benzoic acid, one more H. So up to here, it's OH. The other part is just the organic material part. And just this one has a good crystallization property, easy to use. That's why it's just used. Okay. So basic property, key part here is OOH. Oxidation. With the extra oxidation using this, it insert one oxygen, make a bridged molecule. So this molecule is called epoxide. Okay. Or other name, oxyrain, but epoxide, one name is fine. So this one, epoxide, is reactive because it has a cyclic structure, 3-membered ring. So if there's any nucleophile coming in, attack here and ring open. Okay, nucleophile addition, and this one has a OH as a leftover. So that is a good intermediate. It's a product, but at the same time, that's a reactive starting material. Now, OSO4, osmium tetraoxide, 4 oxygen. Then it's easy to provide 2 oxygen together. Okay? Oxygen, intermediate, cyclic intermediate. And workup, this is reducing agent. SO4 is a fully oxidized form, so this can be further oxidized. That means this can reduce. Reductive other workup means remove OS here and then up hydroxyl can be added here. 이것까지는 몰라도 이걸 보면 OSO4 2 oxygen addition. Product diol. 1,2 diol. Cis or trans? Syn or anti? It should be added like this, right? Syn addition. Okay? Syn dihydroxy. And another modification, this is a reductive workup. Instead of reductive workup, you can add NMO and morphine oxide. Then product is the same. What is the advantage of this reaction? It's a recycling. It's a recycling of expensive OSO4. This is the oxidizing agent, and then this is the basic workup can destroy this reagent, and the product OSO2. That's the dead end. This one can regenerate oxidatively and regenerate the OSO4. Expensive and toxic, and they can be modified by this reagent. Okay, so this is a modified version of OSO4. How about this reaction? Chloroform usually solvent, but if you add strong acid, strong base, chloroform has 3 chloro group. So 3 electron with the drawing group. That means if it has anion here, this anion can be stabilized. That's why this proton is easy to be removed. That means chloroform is acidic. Okay? So chloroform is acidic, so that's why usually chloroform, D-chloroform is a common solvent for NMR solution we will learn in 2 weeks. That solution is potentially acidic. So if your product, if your molecule is acid labile, it's unstable in acid, then you should be careful. In NMR2, the product can be destroyed. Now, once this one in strong base, it can capture this proton, and this minus charge can be removed by one of the chlorine, and the product is very funny. This dot dot product. This dot dot is so-called carbene. Carbene can be attached to the double bond, and it can generate cyclopropane, but in this case, it has a 2-chloro attached. So sometimes we wanted to get cyclic propane, but in many cases we don't want the chloro. So this is a convenient and cheap reagent, chloroform very cheap, solvent, and strong acid. And I think maybe it can be relatively cheap. We can form this cyclopropane structure, that's good, but chloro we don't like sometimes, unless you have a specific purpose. Then the reaction to replace this is starting to use not CHI3. If you CHI3, that's similar to chloroform, right? CH2I2, 2 halogen, the bigger and easier halogen, and then with zinc product, and then it can remove this iodide, and it effectively can generate the CH2 dot dot. Then the end product is cyclopropane as end product, and similar carbene reaction, but there's no chloro. So this reaction is a Simon-Smith reaction. Okay. And epoxide with water to activate it, add a little acid. Then protonation happens here, then that is becoming reactive. Then water can attack from behind. From behind, attack here, ring open, OH, OH. Want to diol. Syn addition or anti-addition? Anti-addition. Okay? Leaving this way and attack this way, anti-addition. Now, product is similar to OSO4 reaction, right? OSO4, syn addition. Oxirane, anti-addition. Okay, epoxide, anti-addition. Now, ozonolysis. Double bond and ozone, and making cyclic structure, and this ozone, now this condition, is that reductive or oxidative? Second, is oxidative? Zinc powder, is that reductive, oxidative? That's a reductant or oxidant? That's a reductant. Metal powder. Metal, the property of metal is giving out the electron permanently, and they become zinc 2+. Giving electron, that's reduction. That's why if you have the reductive workup, and it can cleave this and then give one oxygen here, but reductively cleave off and it generate, if everything is out, then it's ketone. And if it's oxidative, KMnO4, strong oxidant. This reagent you have used to generate oxygen gas. This oxidative reagent, similar property, can break up and it can generate, it seems like the same product, giving oxygen in both sides. Cleave. Okay? But here, if you change the condition, this reaction with here. Now, previously everything is alkyl, then your end product is always a ketone. There's no choice. But if you have proton, the hydrogen each position, then this part, oxygen added, then the product is aldehyde, CHO, but that can be further oxidized because this is strong oxidant. And this side, oxygen is added here, the first product is a formaldehyde. So formaldehyde can be further oxidized, forming acid, and further oxidized, even up to CO2. Whole oxidation condition, it can add oxygen each and further oxidize. Okay? If you change the condition, here, the ozone and the reductive, in this case, previous case, in ozone and reductive condition, adding here, product was the same, ketone. But if this condition, oxidative cleavage generates a fully oxidized product in each side. If you use ozone and reductive workup, then oxygen added here, oxygen added here, no further oxidation, then your product will be here aldehyde, here formaldehyde. Do you follow me? 이게 이번에 배운 것 중에 가장 어려운 부분이야. 이해돼? KMnO4 here, oxygen, and then further oxidation. Aldehyde goes to carboxyl acid. Formaldehyde goes to CO2. Now here, first step ozonolysis, oxygen added in cleavage, and reductively work up. Then no further oxidation, and aldehyde and aldehyde. That's end product. Okay. Now to the diol. To the alkene, if you have the OSO4, 2 hydroxyl group was added, and you can generate this product. And onto this product, if you add a pro-iodate, and then this can cleave in the middle, and you can generate this product. Okay, and so this is a summary of alkene reactions. For the first time, you met various series of reactions, but if you use this summary is in your textbook. Okay, if you look at those summary, and then think about how the reagent reacted with the alkene, then you can follow. 그냥 외우는 거 아니야. 들여다보면서 계속 생각을 해. 어떤 모양으로 접근하고 뭐가 처음에 먼저 생길 건지, 이게 여러분들이 시작해야 될 오게닉 리액션의 첫 스텝이고, 여기서 해내기 시작하면 앞으로 한 7달 정도 계속 해내야 돼. 저기부터 잘 챙기면 계속 연결해서 그거랑 뭐가 달랐지 비교해가면서 하면 유기가 점점 더 재밌어질 수 있어. 오케이, 비교를 놓치지 않게 돼. Okay, so based on this, we move to alkyne. So we just have learned about the double bond, single double bond. Now alkyne is a double bond, the triple bond, right? And then naming first. Double bond we call in. Triple bond we call ine. Alkene, alkyne, right? Like a functional group, like alcohol, something amine. So we treat this as functional group. So alkene, alkyne. So triple bond is alkyne. Okay. So if this alkyne is included, then similar to alkene, ignore the saturated part. You take the alkyne containing the backbone and lower number, and then you choose 1, 2, 3 position here. 3 ine. Older method 3 alkyne to make it a little more systematically, oct separately and oct 3 ine. Both of them are acceptable. Users are substitute 6 methyl 3 octane or oct 3 ine. Either way is fine. If you have both alkene and alkyne, then you can give the name in-ine or I-in, which is easier. In-ine, I-in. In-ine is easier, right? So that's why those naming in first and ine later. And if there are in and ine together, then you include this chain as the main chain. And again, the lower number. Here this is 1 position, this is the 1, 2 position. Then you take this as a lower number. If they are same, 1, 1, then in is higher. Okay? If the numbering in this case, this is 1, this is 1, 2, right? In that case, among them, this is a lower number, you take a 1. In this case, 1, 1. Both of them are the same. If it's the same, then you take in as a higher. Because in is a little more reactive than ine. 따라오는 거지. 도너가 작으면 장부를 택하는 데 섞여 있을 때 번호가 같으면 in한테 우선순위를 준다. Name in ein. In first and ein later. In ein separately, then maybe heptin ein rather than this. This may be a little more systematic. Hept 186 ein. Okay, so this is the naming. Sometimes we need to give that substituent's name. If it is a whole methyl, then we call butyl. If it is alkene, we call butanil. Butynyl. If it's alkyne, butynyl. 익숙하진 않지만 어렵지만지 butyl, butanil, butynyl. If you need to add as a substituent like this. So this is name. Similar rule, longest chain, but double bond, the triple bond included one as backbone, and lowest number. If those probability is the same, then you choose in first, then I. Okay, that's the meaning. 동훈아 왜 이렇게 피곤해? 가지마. 이리 와. Okay, preparation. Triple bond, one reaction. We have learned this kind of reactions. Double bond, and then X2, then 2X is added. Syn addition or anti-addition? Anti-addition, right? Intermediate is a bromine, cyclic structure. There minus attack behind. And on this reaction, if you add a strong base, what do you think? What happens? 잘 모르겠으면 this reaction I showed you in the last chapter. HX and strong base, then strong base attack here and donate, push out and generate this alkene. 살짝 지나갔어. 자세히 안 들고 처음 시작하면서 이런 마음도 있어. 우리는 다음 주에 배우기로. Anyway, if it is proton and bromide, strong base, base attack proton. 그것도 다음 주에 다시 배울 거야. Anyway, strong base attack here. Strong base means electron donating. Donating attack here, push, push. Double bond generating. Then, if you look at this reaction, what do you expect as a product? Strong base attack here, and then push, push out. And that reaction happen again. Base attack here, push, push out. And the end product will be triple bond. Because you have 2x, 1 to x. Okay, if it's 1x, then attack here and then double bond. Now you have two positions. Base attack here, push, push out. One bond, one double bond. And then another one attack here, push, push out. And triple bond. Okay, this is reverse reaction of addition reaction. Right? In addition reaction, double bond, and we add the HX, acidic condition. Because double bond is a nucleophilic. That likes electron 201, that's a proton. Capture proton and X minus attacked behind. That was addition reaction. Elimination reaction is seems like using strong base. Base capture proton and then push and then bromide is released. And that is the preparation to make alkyne. Okay. Look at the step. In the beginning, starting point was alkene. From alkene to alkyne, one step reaction is difficult. That's why you add leaving group first, XX, and then using strong base, you generate the triple bond. 너무 걱정 안 해도 돼. 다음 주, 그 다음 주에 2주에 걸쳐서 이 반응을 자세히 들여다보면서 배울 거야. Okay? Okay, similarly, now here, this is HX, and again, strong base. Previous strong base was a KOH, chip 1. Now here, another strong base we are learning, amide. N minus, NH3 ammonia, NH4 ammonium, NH2 minus, we call amide. Actually, amide has another name. Peptide bond is called as amide bond, CONH. Anyway, N minus is also called as amide. Anyway, NH2 minus is strong base. 동원아, 아마이드는 애시드야 베이스야? 베이스. 정문수도 다 듣고 있죠. Okay, strong base and similar way. Attack here and then push up. It forms similar reactions. Okay. So this is how the alkyne can be prepared. Now let's think about the reaction of alkyne. Alkyne has triple bond. It's not equivalent to 3 bond, right? 1 sigma bond in the middle, and then pi bond. 1 pi bond here, here. Right? The other pi bond here, here. That's triple bond structure. 2 pi bond there. Now here, what do you expect? You have triple bond and HBr. If it behaves similar to alkene. Again, H can be coordinated here, and Br minus may attack, right? Then 1H, 1Br attached. Is that Markovnikov or anti-Markovnikov? It's Markovnikov, right? More substitute position is added here, similar way. If it goes further, if you have HBr further, then you will get 2 addition. So this reaction we have done. Now, from alkyne moving to this, it's a similar reactions. Right? Similar reaction, it can go. Triple bond also can take HBr. Okay, for the original HCl. Now, if it has option, then this HCl addition is that syn addition or anti-addition? It's anti-addition, right? Protonation first, and then Cl minus attack behind. That's why the product in principle can form trans and cis mixture, but in this case, it has only one product can be formed, anti-addition. Once the alkene is formed, then HCl is similar way Markovnikov product moving forward. Okay. So this is the anti-reaction. And this is, even though this is a trans, G is a 주잔면, so together. E is anti-gegen, it's opposite. 주잔면 sounds like a cis, but in this case it's not. This is a trans, but this is a 주잔면. The rule is different, right? Which is the higher here? C. Cl is the higher. That's why this is a higher. Among these, this is a higher. That's why that's a C. Right? Okay, here Br2 addition. We already have seen similar pattern. Br2 again, Br and anti-addition. That's why this is the problem. Okay, chromium as intermediate, and then it can form. And if you have more Br2, then we can finish up those reactions. 알킨 배우고 나니까 알카인은 극히 서로는 떨어지고 파이반드가 두 개 있다는 걸 알고는 지금까지는 알킨하고 거의 같은 행동을 보이고 있어. Okay, reaction mechanism again similar way. Alkene case, carbocation was intermediate, and alkyne case, once this is formed, this is so-called the vinyl. This double bond is a vinyl cation is formed, but behavior is similar. And carbocation case, the center was sp2, planar structure. In alkyne case, intermediate is still double bond there. So the other position here, this is sp2, this is sp. That's slightly different. But still, product-wise, it behaves similarly. Markovnikov law is followed. Okay, hydration reaction. So what did we learn? HX addition and X2 addition. Okay. That's what you have learned. Hydration, adding water. Water addition is a little different. Now this condition, acidic water or mercury water, that's Markov-Nikov product, correct? Hydroboration, anti-Markov-Nikov hydration. Here, first product is, if you add this one, OH added where? This more substitute position, right? This is intermediate. If it goes further, maybe OH should add here again, but this intermediate, if you look at, this intermediate is, funny way, this intermediate is alkene with alcohol, so-called enol. This is called as enol. This is, can be rearranged quickly, can form this kind of a ketone form. Now this relationship, is this resonance? If it is not resonance, why not? Why this is not resonance? The proton was moved, right? This is equilibrium. This is a kind of isomerization. Among isomers, only proton was moved. Proton is lightest atom. That's why the movement is faster than any other atom. It's slower than electron. Electron is much lighter, 1,000 times lighter. That's why electron movement always we cannot see. That's why we call them resonance. But proton movement is much slower than electron. We can detect this one, and this arrow means this is equilibrium. And this is shifting to this way much further. This is more stabilized than this one. That means once this intermediate is formed, it cannot go next reaction. Next reaction is OH added here. Without going there, it moves rearranged to generate this ketone form. One hydroxyl addition and reaction is finished to go to here. Okay, that's a slightly modified version. Alkene case, if you add this reaction, double bond has one hydroxyl, one proton. That is the alkene product, right? If it's a triple bond, one addition of a hydroxyl that can be rearranged to go to ketone form. That's the difference. Okay? So this is the mechanism, how it goes. Now, here. So to summarize here, if it's this case, now you have a chance to add a hydroxyl here or here, not much different. Then you can get maybe mixture. If it's a terminal position, then definitely water will go this position, and OH here and then double bond here, and then rearrange to generate this ketone. Okay? We have seen similar cases before. If it's a Markov-Nikov product, both of them is the same substitution of the number, then you will get mixtures. Similar situation here. If it's a dominantly one side is H, one side is a kill, then hydroxyl goes here, and rearranging the product generate ketone. If water goes this position, then what you get? Aldehyde. But that is not Markov-Nikov product. Markov-Nikov product generated ketone. Then, if you use anti-Markov-Nikov rule, hydroboration, then the product will be aldehyde. Right? Because the water, OH was added, sorry, this is not the case. Page so in this case, if there is terminal position, BH2 can be selectively added here, and then that position is a hydroxyl added, then this position will give you aldehyde as a product. So Markov-Nikov product, OH is added to more substituted position, and that generates the ketone as the product. Anti-Markov-Nikov, hydroxy is added to end position, because that the end position that generates aldehyde as the product. Okay, so this is the version of alkyne reaction version of Markov, anti-Markov-Nikov dehydration reactions. Okay, so this is summary. If it's both sides are similar, then you will get mixture anyway. If one side is terminal, means hydrogen, the other side is alkyl. Mercury condition or acidic condition, acidic hydration, you will get this product, ketone. Hydroboration condition, OH is added to this position, and then that's rearranged to generate the aldehyde. Okay, OH position is different. One is here, this one is here. Okay? Okay, reduction. 자, 지금까지 뭐 배웠나 생각해보자. HX addition, X2 addition, and hydration. 저랑 세 개 배웠어. 알킨하고 거의 비슷해. 이런 거. Reduction. In alkene, the reduction was what? Palladium catalyst, hydrogen addition, syn addition, right? Similar reactions can happen in the alkyne too. Now, if you look at this energy released, which step is more exothermic? First reaction or second reaction? Which reaction is more reactive? First reaction or second reaction? First addition or second addition? Which one is more reactive, you think? First reaction, because it's more exothermic, right? It generates more heat. That means first reaction can be more reactive than second reaction. It has a 2 pi electron. If it is reduced by hydrogen, first reaction can be more reactive, you can assume. But if you do not control, then this reaction is usually, second reaction is also quite effective, easy reaction. You can go to the next step. So sometimes you don't want to change alkyne to the alkane. Alkene is a more useful reagent, more reactive. So you want to stop here. Maybe doable, because first reaction is more reactive. If second reaction is more reactive, no choice. Right? As soon as the first product is formed, it can go to the next step right away if it is more reactive. But in this case, first step is more reactive. Then if you control those reactivity, then you can stop the reaction here. Now, what was the catalyst for hydrogenation in alkene? What is the catalyst of hydrogenation? 오늘 벌써 두 번이나 얘기했는데. 금속 surface. What was that 금속? Platinum or palladium, kind of a metal surface. Okay. Now, to make this the catalyst a little less reactive, they add some funny poison, quinoline or lead acetate kind of reagent to this palladium powder. So it has been developed by Lindler, it's the name of a chemist too. The purpose is, if that catalyst is too efficient, then the reaction cannot stop. It can just move to the end point. So I don't want to let it go to the end product. I want to stop here. So he tried to add some poison to the catalyst. No catalyst, no reaction. Too good catalyst, it goes to 2 steps. I want to start the reaction in the middle. So he tried to add any kind of funny way, poisons to the catalyst to suppress the reactivity. And he found by adding quinoline or lead, not acetate. Then he found some composition. It's not molecule, it's just adding 1% of lead, 2% of quinoline kind of composition. 무슨 요법 같은 거지, recipe. And then he found his own the catalyst called the Lindler catalyst. And using these conditions, really, this reaction can go to one first reaction and stop it. Again, this is syn addition or anti-addition? 더블럭 말하던 this is the same way, right? This is syn addition. So that's why it forms this same product. If you want to move forward, then you can use original catalyst, palladium. Palladium-C means to activate the palladium, make the powder, and absorb them into charcoal. Charcoal is like a surtan, but it's activated the material, make with a lot of porous structure by heating, remove the water and the gas, it has large surface area charcoal, but the carbon is called as the charcoal. PDC means it is deposited on the surface to generate maximum amount of surface area. Okay, so this is the activated catalyst. This is poisoned catalyst. With this, you can stop here. With a good catalyst, you can go further. Okay? Good catalyst, you get a very cheap material. That's why sometimes you want to control the reaction stop here. Okay? That reagent is called as a Lindler catalyst. Except that, it's anyway, that's addition reaction of hydrogen. Now, if you use this kind of a Lindler catalyst, double bond, double bond, double bond, triple bond, then only this step, this the double triple bond can be one step hydrogenated and cis form because it's a single addition. Okay. Now you have multiple reactive groups. You need to think whether I can do only reduction on here. In this case, if you use a PDC, not a Lindler catalyst, then what do you get? Donut, what do you get? If you use a PDC here, what is your product? Then all the bond here, they will be fully saturated alkane. Okay? That will be your product. Okay. Now, this case, catalyst was solid metal. It's a syn addition. That means two hydrogen is added together. And how many electrons are donated? 2 electrons. H2 has a electron in the middle. That electron is not donated by metal. Metal is just catalyst. Okay. This 2 electron and this 2 pi electron, they made 2 new bonds. Right? That's a syn addition. 4 electron made 2 bonds, 2 new bonds. It's a similar reaction, but if you use this kind of condition, ammonia is like water. OH2, NH3. You can expect that they may be quite similar, even though this is a little more basic. It can be a lipid at low temperature, minus low temperature. If you dissolve metal here, now in this case, NH3 is like a solvent. Now reagent is a lithium. That lithium, is that nucleophile, electrophile, oxidant, reductant, acid, or base? Hmm? It's a reductant? Really? Why?
리튬은 이게 우주적으로 에lectron 줄 수 있어.
And then the product is LiH, lithium plus, that's product, that's reductant. And lithium can donate how many electrons? It's a single electron. On the palladium surface, if the palladium activates hydrogen, one bond is activated, and then 2 electron there, 2 pi electron here, those reacted together, rearrange to make a new bond, right? There's a 2 electron at least involved here. Lithium case, it is dissolved in NH3 and becomes Li plus and donate only 1 electron. So the reaction happens, and then the proton source is from NH3's H. Proton is reduced and then added, but that's 1 by 1. Intermediate is 1 electron is added, that forms this kind of a funny radical anion. And added 1 by 1, that's why there's no reason to be added the syn addition. Add 1, and then less reactive side is attacked behind. It can react as giving the product as an anti-product. So here, if this reaction happens, not syn addition, adding 1 rather than 6, the trans is more stable. So more stable trans is formed because of one step, 1 by 1 is added. 1 proton captured 1 electron and added, and another proton captured another electron and added, and intermediate is rearranged to open more open space, then it ended up as this kind of anti-addition. Okay, so reduction reaction we learned two now. Hydrogen activated by metal surface. That's one reduction we learned. But definition of a reduction is electron donation is reduction, right? Permanently. Then metal powder, they can donate electron. So lithium in ammonia is one typical example. This kind of reagent they say dissolving metal. Metal is dissolved in protic solvent, and then it can slowly changing into lithium plus, and then donate electron one by one. In the case, the product is the more stable and the product. Not cis form, it forms transform. Okay, two reductions we have learned. Oxidation. In alkene case, oxidation we have learned various cases. Oxidation case, when we use this kind of condition, ozonolysis or permanganate, it break up the double bond and then generate ketone. If it is the oxidative workup, sorry, the ketone is the common. If it's the H involved, one side can be carboxyl acid or CO2 kind of conditions. In triple bond, the similar way, it can end up with oxidative conditions which generate carboxyl acid or CO2. If it is fully the protective side alkyl-alkyl, then it ended up as ketone. But these reactions are not very efficient compared to alkene. So even though they behave similarly to alkene, but this reaction is not practically useful. So up to reduction is useful reactions. Okay, up to here. 자, 샥 달려왔는데 알킨하고 알카인은 서로 비슷한 면이 많이 있지만 약간 다른 것들이 있었지. 많이 배운 것 같지만 4개 배웠네. HX X2 addition, water addition. Water addition, one water is added, then enol is formed, rearranged to generate ketone or aldehyde. And then we learn reduction. Reduction two kinds. Metal surface, hydrogen addition, syn addition. The other one, dissolving metal, donate one by one. Then more stable product, not cis form, transform. That's all. 정리하면 충분히 정리할 수 있는 양이야. 자, 지금이 고비니까 열심히 문제 풀고 헷갈리는 부분들 자꾸 비교해가면서 확인해야 나중에 봤을 때 안 헷갈릴 수 있어. 내 경험상 문제를 3번 풀어봐야 정리가 돼. 3번 풀 때는 알 것 같으니 다시 돌아가면 막 헷갈려. 뭐가 뭔지. 2번 풀면 반점하고 반점 몰라. 3번 풀면 이제 대충 시험 볼 때 한 번 더 보면 이제 평생 가지고 왔으면 문제 생기네. Okay? Any question? Okay. 그러면 앞서 here.